I just gave you is me keeping the promise from last time. Okay, remember last time I promised you that I'm going to show you a coding scheme that will make sure that there's the symbol error rate and bit error rate are one the same. When we looked at probability of error, all the formulas that we derived were based on probability of symbol error. Right? We were talking about going from S1 to S2 or S2 to S3, right? That you're making a mistake in interpreting the symbol. Now, we know that symbol carries a lot of times more than one bit, right? If we have 8 symbols in our constellation, how many bits are packing on each symbol? 3. So the question that we need to ask is, how do I encode my symbols, or how do I perform mapping between bits and the symbols so that whenever I make mistake on a symbol, that does not translate in more than one erroneous bit? And the answer for that is grace coding. And the sheet that I gave you teaches you how to make a gray code. But let me first highlight the code. Let's say, so I'm going to actually just use an example. And the example I'm going to use is going to be 8 level pulse amplitude modulation, 8 pump. Now, how does the constellation in the case of 8 pump look like? It's a one-dimensional signaling, so all of the constellation points are going to be on a plane. So you're going to have a situation like this. This is your 0. So you're going to have 1, 2, 3, 4. Is it enough? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 8. Right. So those are your 8 symbols that you're going to have. Let's make an attempt to encode these guys using natural codes. So natural meaning, you know, how we just count in binary, 0, 0, 0, 0, 0, 1, 0, 0, so on. So let's try to do that. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, no, 1, 0, 1, right? 0, 1, 1, 1, 0, and 1, 1, 1. So let's say I've sent this symbol here, but by mistake I received this one. How many errors am I making? 3 bits erroneous, right? So look at this. This is a specific. This is a dangerous mistake, right? So how do I avoid this? Well, what I need to do is I need to design a code where the difference between adjacent symbols is exactly 1 bit. And the code that satisfies this property is the gray code. Gray code, you have an algorithm on this sheet of paper that I gave you. But the way how you design it recursively, I'm just going to go through a couple of iterations here. You start, gray code only exists for these powers of 2, right? So you can start with n equal 1, n equal 2, so 2, 4, 8, and so on, right? Code words. So for n equal 1, I start with 0, 1. That's a great code for n equal 1 because if you make erroneous mistake, they are only different by 1 bit. The thing here is that's also one symbol, but that's kind of besides the point. Now if you go to n equal 2, you're going to have 4 symbols, each one of them carrying 2 bits. So the way how you design the coding words for n equal 2, you're going to take these 2 and write them again, and then you're going to put a mirror here, and then write what is seen in the mirror, right? So this is 0, 1, 1, 0, right? Here's a mirror. And then you're going to take to the upper ones and add zeros, and then you're going to look at the lower ones and add ones. So this becomes 0, 0, 1, 1. So if you look at the difference between these two is 1 bit. Difference between these two is this 1 bit. Difference between these two is 1 bit as well. What you don't see here, but we'll show that this is of a great use later, is the difference between these two guys, the first and last, is also 1 bit. Right? It kind of wraps itself around. Let's take it one more time. So n equals 3. You take whatever you have here, you repeat it once again. 0, 0, 0, 1, 1, 1, 1, 0. Here's the mirror. And then you do that again. So it is 1, 1, 0, 0, 0, 1, 1, 0. And then you add 0, 0, 0, 0, 1, 1, 1, 1. So if you test now these codes, you will see that the two adjacent ones are only different by a single bit. So now I can, and also the last one and the first one are different by a single bit. So instead of encoding these 8 symbols with a natural code like I indicated here, I'm going to encode it with a gray code. So it becomes 0, 0, 0, 0, 0, 1. But instead of 0, 1, 0, I have 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. So in this case, so this is natural, and this is gray code. So in this case, you can see that wherever you make a symbol error, if you go to anyone, let's say you send this one and you interpret it with this guy, you're going to be erroneous on only single bit. Or if you go the other way, so you're going to be erroneous on single bit as well. Therefore, if you do encoding with using a gray code, the symbol error becomes the same as a bit error. And you've got to be aware of this, because a lot of times those waterfall curves, we tend to be sloppy, right? So we say, okay, this is a symbol, the probability of error, not saying whether it's a symbol error or a bit error. And really what you need to know is that if you do the encoding properly, these two become the same, right? Because one symbol translates into 1 bit error, even though you're packing more than 1 bit on a single symbol. Okay? Any questions here? Right. So, just I have extra copies here. All right, so let's pick up where we left off last time. What we covered last time, we showed how you calculate the probability of error in a one-dimensional scheme, and we kind of carried that all the way through and have a single expression that we derive for all level pulse amplitude modulation. What I'm going to do today is show you how you do that using two-dimensional signaling, in the case of two-dimensional signaling. And namely, I'm going to talk about PSK. PSK is a simpler of the two-dimensional signaling. You're using the two vectors that you have, but in a restricted fashion. Every symbol has to be on a circle. You know, it is a little bit less constrained when you have QAM, right? QAM pretty much can pick any point in a constellation plane. As a matter of fact, if you want to be strict, PSK is a special case of QAM, right? Where you're just restricting the points that you pick to be on a single circle. So let's take a look at how you calculate the probability of error here. So probability of error in phase shift key. In phase shift key, your points, so this is your psi 1, this is psi 2. All the points reside on the same circle, which means that all the symbols that you use have the same energy. Remember, because the distance from the origin is the square root of energy. And these are your symbols. Let's say, for the sake of example here, I'm going to draw 8 BPSK. So I have 8 symbols that are shifted pi over 4 from each other. Now, what I need to do is form a decision boundary here. How is the decision boundary look like? In other words, what is it that I'm asking? If this is the Sn that I have sent, where do I decide if R falls in which region? I would decide that this was Sn that has been sent. And what is the inside the decision boundary and what is outside? Since we are basing our decision on a maximum likelihood, assuming the equal probabilities between the symbols, we're going to actually draw the boundaries just like we expect them to be, based on the distance, Euclidean distance between the received symbol and the constellation point. So the decision boundary here would look like this. Right? These two are in the middle between the two adjacent symbols. So this is your Sn minus 1, and this is Sn plus 1. Right? So whatever falls within this area here, this is your, how do I call this, RC? No, R. And this area outside is your R complement. So what is the probability of error? Probability of error is going to be an integral over R complement of the PDF of R given that Sn has been sent. So that's the probability of error. I'm going to have probability density function of the received symbols under condition that Sn has been sent. So that will be, that curve, or remember that bell that comes out of the board, and it kind of tells you the distribution of the points around this one. And whenever the point falls outside of this R, which means I'm integrating this PDF over R complement, and that is going to be the probability of error. Okay? So let's, now this is, I guess, an expression in general. Let's do this in this particular case. And what I'll do is I will actually go ahead and kind of calculate this. And you will see it becomes a little bit cumbersome. It's not particularly hard. It's just that the expressions are long. And we're going to get the closed form solution. But that's just as far as we can go. Right? You will see that in every, even if I complicate this a little bit more, then you will see that it becomes analytically very difficult to do. Go ahead.
You have a integral of PDF. Is that a CDF actually?
No,
so you're
it's a
looking for
PDF. PDF. You rarely integrate CDF. It makes no sense. PDF is the density. So you integrate the volume underneath this surface, right, to get the probability. Okay, so let's remember some couple of things here. Phi m is equal to 2 pi m over capital M, where m is equal to 0, 1, 2, all the way to m minus 1. So these are these, if it's a m level PSK, then you're going to have n different angles that are all separated 2 pi over n, where n is the total number of symbols in your constellation. Sn is going to be a vector that has distance square root of energy, but has a coordinates cosine 2 pi m over m, and then sine 2 pi m over capital M. So that's this particular vector here. And then the decision boundaries are like this. Let me call this one T1, and this is T2. T1 is going to be 2m minus 1 times pi over m. and T2 is going to be 2m plus 1 times pi over m. So these are the two adjacent boundaries in terms of m and I guess 2 pi over total circle. And then this guy here can be rewritten more specifically. Let me just rewrite this as 1 minus probability of error given that Sm has been sent as an integral, which is now probability of making a correct decision, right? 1 minus probability of error. So I'm going to, instead of integrating over r's complement, I'm going to integrate over r, right? Which I can kind of say that this is the same, this probability of error, right? Is the same as 1 minus integral over r PDF of r given Sm dr, right? So I can integrate it either over the r complement, in which case I'm getting probability of error directly, or 1 minus probability of making a correct decision. So 1 minus probability of making an error is the probability of making a decision. So this is, I'm going to integrate over this pizza slice, right? Infinite pizza slice. So I'm going to say rho goes from 0 to plus infinity, and then some angle, right? So what angle? Let's say angle phi goes from T1 to T2. And this is now phi. PDF of r given Sm, and then the element of the surface, right? Which is going to be rho d phi. This will, in the polar coordinates, this becomes rho d phi. I know you've seen that somewhere.
Jacobian.
Say again?
Jacobian.
Yeah. This is Jacobian. If you when you transfer it from the Cartesian coordinates to the polar. Okay, so this is what we need to evaluate. Okay, so the first thing that we need to determine, well, what does this PDF look like? Do we know how to write this expression? And we do, because we actually analyzed our dart throwing guy, and what we know here is that when I throw darts, they're on average unbiased, so I'm forming a circle around it. I know that on average I'm hitting this point, so there's expected value of the noise is 0. I know that that it's a circle, so I'm the same in every direction. I know that these noises are uncorrelated across different directions. And I also know that the standard deviation of that noise is square root of n0 over 2, where n0 over 2 is the double-sided power spectral density of the thermal noise at the input of the matched filter. So, since based on all of this, I can write something like this: PDF of R. Now, I have a justification to write vectors here, right? Because this is all in 2 dimensions. PDF for R given Sm is going to be equal to pi product when k goes from 1 to 2, PDF of Rk given Smk. I can write this because the errors along the 2 different coordinates are independent, and therefore the joint probability is product of the marginal probability density functions, right? So I get this as a product of these 2. But I actually know what this one is. So PDF of Rk given Smk is going to be equal to 1 over square root of pi and 0 e to the minus Rk minus Smk squared over n 0. Okay, k is 1 over 2 because this is a 2-dimensional signal. So since I know that these 2 probability density functions, then I can form this joint probability density function here as PDF of R given Sm becomes product of these two, so it becomes 1 over pi and 0 e to the minus R1 minus Sm1 squared over n0 times 1 over square root of pi n0 e to the minus R2 minus Sm2 squared over n0. So that's a joint probability. That's the function product of these two. What product I'm talking about? Remember when we looked at this in general case, there's this probability density function along this coordinate, and then along this coordinate there's another one that looks like this. They're identical in terms of their width, and they're just centered around this point. So if I take the product of these two, then you end up with that belt that comes out of the board that I'm trying to describe with this particular equation. Where this is psi 1, psi 2, and so. All right, so let's simplify this a little bit. So I can, since we know Sm1, I guess Sm1 is the square root of, let me put this as a symbol energy to make sure that you understand that. So this is epsilon s cosine 2 pi m over m. And then Sm2 is going to be square root of epsilon s sine of 2 pi n over m. These are the two coordinates associated with this point Sm. Right? This is the projection on the psi 1. This is the projection on psi 2. Now, if I plug this in here, and obviously this times this gets rid of the square root, and then e to something times e to something else is e to sum of the two. So this can be simplified to look like this. PDF of R given Sm is going to be 1 over pi at 0, essentially this times this, minus, times actually exponent of minus. Downstairs I have n0. And upstairs I have R1 minus square root of epsilon s cosine 2 pi m over capital M, but the quantity squared, and then plus R2 minus square root of epsilon s times cosine 2 pi m over m quantity squared. Okay? That's a little clumsy notation, but let's look what it means.
Isn't it sine?
Huh? Yeah, this is sine, sorry. Sine. So let's understand what this means. Let's say this is my Sm. This is here Sm1, and this here is Sm2, right? This is psi 1. Psi 2. Now let's say this is R, right, which has coordinates R1 and R2. So what is it that I'm doing here? I'm taking R1 minus Sm1 squared plus R2 minus Sm2 squared. So what is it that I'm actually calculating?
Error. Noise.
No, no noise. I'm calculating, look at this in a vector space. First coordinate minus first coordinate squared, plus second coordinate
Distance.
minus second
Distance.
distance squared, right? So I'm calculating this distance, right? That's what I'm calculating. So what I have here is the distance squared between R and Sm. Do you see that? All right, so I have essentially this being equal to 1 over pi and 0 times e to the minus distance squared between r and Sm divided by n0. So that's the format of my PDF. So what is left? I need to take this, put it in here, and hope for the best. Let's see if I can get that integral evaluated. Okay? So let's do that. I'm going to leave this picture for the reference, but I'm going to erase the rest of it. So let me, before I go and substitute, let me actually do one more thing. R, which I was saying is R1, R2, I'm going to write this as rho e to the j phi, right? Where obviously this rho is square root of R1 squared plus R2 squared, and then this phi is R tangent, I want to put 2 of R2 over R1. In other words, I'm going to express my received point R as in polar coordinates, as rho, as the distance from the origin, e to the j phi angle that it forms with the psi 1 axis. Then the distance d between R and Sm can be written as magnitude of rho e to the j phi minus square root of epsilon s e to the j m times 2 pi over capital M. Right? And then square it here. And put that on this. So I'm going to substitute this instead of just d squared. This is the square of the distance. And the reason why I'm doing that is because I'm switching to polar coordinates because of the symmetry of this problem. It is much easier to integrate in a polar coordinate than to try to worry with x and y. So, therefore I have something like this. 1 minus probability of error given that Sn has been sent. I'm going to say it's rho going from 0 to plus infinity. Phi going from T1 to T2. 1 over pi and 0. E to the minus magnitude rho e to the j phi minus square root of epsilon s e to the j 2 pi m over capital M squared divided by n0. So that's my PDF. And then I have to add the element of the area, which is rho 0 d phi times. So that's the whole integral that I need to evaluate. So one thing that you realize, if I determine the probability of error for any given Sn, it's the same for all of them, right? Do you see that? Because of the symmetry. All of these are the same. Since the problems are equiprobable, the symbols are equiprobable, then I have an average of m same numbers. So average, if I take m same numbers and I take the average, is the same as each one of them. So the probability of error given Sm is actually the same as the probability of error in general. Right? Because I have m equal probabilities of error. If I take the average of that, then I get one of them. So I can say, so given that that's the case, then I can simplify my calculations by saying that since probability of error is the same for every m. Let's pick up, let's calculate it for m equals 0, right? So why m equals 0? Because then this goes away, and that is helping me somewhat in making this expression simple. So 1 minus probability of error given S0 becomes integral when rho goes to 0 to plus infinity. Phi goes, now this is minus pi over m to pi over m. If you remember, the phi was 2m minus 1 times pi over m. Well, if m is 0, then it becomes just minus pi over m. And this one was 2m plus 1 times pi over m. So if m is 0, it's just pi over m. And then this becomes 1 over pi and 0 e to the minus rho e to the j phi minus square root of epsilon s squared over n0 rho d rho d phi. And so that's now an integral that we need to evaluate. So let's obviously the thing that is the most cumbersome is this expression here. So let's see if we can simplify this one somewhat. So the magnitude of given, consider this following: magnitude of rho e to the j phi minus square root of epsilon s squared becomes rho e to the j rho j phi, sorry, j phi minus square root of epsilon s multiplying rho e to the minus j phi minus square root of epsilon s. Why is it that I can write this? Because the magnitude square of the complex number is the complex number times its complex conjugate, right? So that's what how I can simplify this. But then if you take this one step further, you get rho times this, so this becomes rho squared minus square root of epsilon s. Then you have rho e to the j phi plus e to the minus j phi, and then divide by 2 and multiply by 2, and then plus square root of epsilon s quantity squared. See how things surface. All of our good friends start showing up here, cosines and sines and so on. So this ends up being rho squared plus epsilon s minus 2 times square root of epsilon s times rho times cosine of phi. So that's a simplified version of this magnitude squared over there. So now if I plug this into the expression, I get 1 minus probability of error given S0 is going to be equal integral when rho goes from 0 to plus infinity. Phi goes from minus pi over m to pi over m. And then you can see here, okay, so I'm going to write this 1 over pi, and then write this as e to the minus rho squared over n0 plus epsilon s over n0 minus 2 times square root of epsilon s over n0 times rho over square root of n0. I think it's a mistake here in the notes, right? Right, because when you take this n0, divide, give square root to this guy and square root to this guy. So it's going to be rho over square root of n0. And then cosine phi, and then rho over square root of n0, and then times d rho over square root of n0, and times d phi. So that's why am I grouping in that way? Obviously, there are some substitutions that I would like to introduce. This is one of them, rho over square root of n0. The other one is square root of Sn over n0. So substitution. Epsilon s over n0. I'm going to call that rho s squared. And rho squared over n0. I'm going to call that equal nu squared. So now probability of error given as 0 becomes equal 1 minus this. So 1 minus 1 over pi goes outside. And then integral when phi goes from minus pi over m. I didn't mess with phi, so I'm just going to put it here, pi over m. Pi over m. And then integral here. Now, when rho goes from 0 to plus infinity, what happens to nu? It's the same thing, right? Nu goes from 0 to plus infinity. And then I have e to the minus nu squared plus rho s squared minus 2 nu rho s cosine phi nu d phi. Okay, so with every step it gets a little bit better at that, right? So you just have to hope that
Reduce it.
originally that eventually it will kind of converge. Now, what happens here is this, in general case, doesn't have a solution. So there are two cases for which it does. So even this case, when m is different than 2 or 4, does not have a solution, right? Or doesn't have a closed form solution, I should say that, right? So let's let's look at the cases where this has a closed form solution. So there are two of them. Call this star. The integral in star has a closed form solution. For m equal 2 and m equal 2. Let's tackle m equal 2 first. Why do we tackle m equal 2 first? Because we already know the result of that one. We just want to make sure that what we did so far is accurate. Right? What is m equal 2? If m is equal to 2, I have this guy and this guy. How do we call it? BPSK, right? And for BPSK, we derived the probability of error. It was Q over square root of S and R. Remember? So that was, we should get the same result here if we did everything correct. So now, if you have n equal 2, then probability of error given S0 was going to be 1 minus 1 over pi. Now phi goes from minus pi over 2 to pi over 2. Nu goes from 0 to plus infinity. Note that here my decision boundary, is the y-axis. Pretty much everything to the right of it qualifies. But I'm doing two-dimensional signaling, so my error exists in a 2 dimensions, even though my signals are all along 1 dimension, right? So now I have this e to the minus nu squared plus rho s squared minus 2 nu rho s cosine phi nu d nu d phi. And now if I introduce substitutions, nu cosine phi is equal to R1 and nu sine phi is equal to R2. Then nu squared is equal to R1 squared plus R2 squared, and nu d phi is dr1 dr2. What am I doing here? Going back to Cartesian coordinate system. So because of the nature of the problem, it's not doesn't have the circular symmetry anymore. So we integrate in Cartesian coordinates. So if you do that, you get the probability of error given as 0 is going to be equal to 1 minus 1 over pi integral when R2 goes from minus infinity to plus infinity, and R1 goes from 0 to plus infinity. And I have e to the minus R1 squared plus R2 squared, that's that nu squared, plus rho s squared minus 2 R1 rho s cosine phi, and then I have to say, no, this rho s cosine phi is R1, so rho s, and I have to do dr1 dr2. Now this separates into two integrals. The first one is, so this becomes 1 over square root of pi. Integral where R2 goes from 0 to plus infinity. Let's just assemble whatever is with R2 here. So this becomes e to the minus R2 squared dr2. And then times 1 over square root of pi integral R1 goes, okay, this is not from 0, it's minus infinity. So R1 goes from 0 to plus infinity, e to the minus, and then if you look at here, you have essentially R1 minus rho s quantity squared dr1. Okay. Now, one thing that I don't know if you know this integral, let's call this integral from 0 to plus infinity e to the minus x squared dx. Do you know how large is this integral?
Pi.
Close.
1 over pi. 1 over square.
Yeah, it's a square root of pi
Pi.
divided by 2. Alright, so if you look at here, you have two of these guys. So because I can integrate, this is even, right? So it's 2 times from 0 to plus infinity. So it's 2 times square root of pi over 2. And 2 and 2 cancel, square root of pi and square root of pi cancels. So this whole thing here is equal to what? 1. Now, this is mathematically, but what is physically? Why is it equal to 1? What is the R2 coordinate? It's this coordinate, right? So it cannot depend on that, right? Because remember, you have two, the noise along this coordinate doesn't do anything, right? It doesn't sway your decision. You know what I'm talking about. Like if you're having two, you're having an m equal 2. So here's your constellation point. If I'm throwing a dart, offsetting dart in this direction doesn't do anything. Right? It is this direction that is critical. Right? So this is R2 and this is R1. So this noise in this direction doesn't do anything. So that's why this is equal to 1. Now, the second one is more interesting. And so I get the probability of error given as 0 is going to be equal to essentially 1 over 1 minus 1 over, let me just do the square root of pi. Integral R1 goes from 0 to plus infinity, e to the minus R1 minus rho s squared dR1. And then I, again, do substitution, where I say R1 minus rho s is equal to x over square root of 2. Therefore, dR1 is going to be dx over square root of 2. So that substitution gives me 1 minus 1 over square root of pi. When R1 is equal to 0, where is x? Where is x? This is equal to 0. So x needs to be square root of 2 times, minus square root of 2 times rho s. So x goes from minus rho s times square root of 2. When R1 is plus infinity, this is plus infinity. And this becomes e to the minus x squared over 2 dx. What is this? What am I, okay, dx, and then I have to have here square root of 2. Now take the square root of 2 from here and bring it underneath this pi. What does this look like? Gaussian, right? So this is upper tail normal for minus rho s square root of 2, right? So let me just draw this a little bit so that we make sure that what I have here notes is correct. So here's what we need to evaluate. This is our normal distribution. This point here is minus rho s times square root of 2. Now this whole thing is upper tail normal, so it's from here to the right. Okay? But 1 minus that is what? Is this, right?
No.
Right, so this is our probability of error given S0 has been set. And this is going to be equivalent of this. Where this here is rho s square root of 2. Right? Do you see that? So the P of probability of error given as 0, this becomes Q, or upper tail normal, of rho s square root of 2, or Q of rho s square root of 2. So that's our final expression. Now, what we need to go back and remember, what was this rho s? Recall, rho s, I defined it as square root of epsilon s over 0. Therefore, rho s times square root of 2 is going to be square root of 2 epsilon s over n0, which is square root of s and r, and the output of your next filter. So probability of error here, given S0, which is the same as probability of error given probability of error for S1, which is the same as probability of error, is going to be Q over square root of S and R, which is what we expected, right? We'd better beat that, right? Because, you know, the fact that we are calculating it differently doesn't change the end result. We already did this a different way last time. Now, if I go now to m equal 4, and if I'm patient and diligent and knowledgeable enough on integration, you should get probability. I would get probability of error as 2q over square root of 2 epsilon s over n0. Again, our s and r. And then here 1 minus 1 half q over square root of 2 epsilon s over, actually, sorry, it says dv here. dv over n0, where this EV is equal 1/2 over epsilon s. Now, so there you have it. What do you think about it? It's a nightmare, right? You know, it might be, you know, if you're mathematically inclined, which all we are, but to the point where you kind of have want to test yourself and spend some time, you know, remembering calculus 3, you would want to go and calculate this. But in general, you know, that's not what we are here for. We need to understand what the probability of error is. And the fact that you can only calculate it analytically in these small number of cases, what if m is equal to 8? You cannot even do it, right? So the fact that you are limited to just few cases teaches us that we have to do it alternatively. We have to do it through some sort of simulation or some sort of numerical integration. Now, you still want to do it once because you want to understand where it's all of this coming from, get some intuitive feel. But in practice, you always resort to some sort of simulation or some sort of software to do that. Now, so let me put some notes and then I'll talk a little bit more about simulation. So, notes. First, evaluation of probability of error, simple conceptual. Right? I told you that maybe 2 lectures ago. There was that integral, and I said, hey, all you need to do is get this integral evaluated. Right? That's the end of theory. Now, from that point is where the practice picks up. And sometimes you can evaluate it, sometimes you cannot. But at any point, should be no doubt about what is it that you're actually doing. You're trying to integrate the conditional probability density function over the complement of the decision tree. Right? So you make your decision boundaries, you identify the complement of decision for a given symbol, and you have to evaluate your probability density function. Probability density function in the case of the Gaussian noise is very simple. It is equal to the product of these marginal probability density functions where every coordinate is independent of every other coordinate. So it is very easy to write it out, at least before you start tackling the integral. So, but the second bullet here is complicated analytics. And the third point, usually done Okay,
Okay, I have a question.
go ahead.
I have a question. So in this case, whenever we want to calculate the probability of error in PSK, which part that we should remember? I mean, like the probability of error is equals to Q square root of SNR, like some from previous
Okay.
lecture you told about no.
I can tell you which one I remember, right? I remember this result. This is, appears quite often. And you just, if you do
Use the upper tail
enough
and
of
lower
these
tail.
problems, you just remember it, right? The rest of it, you don't. This is even, beyond normal remembering. I mean, if you go and sit down and learn it, you will remember it, but in
Is it the
6
same?
months, you will
Yeah,
not.
it's same. You just like multiply it for with a n equals to 4, right? You just
No, this is
divide
for
it.
m equal 4. It's similar, right? But it's not
Right.
the same.
You multiply it inside, it goes back.
How does it go back? Does it go back? There's
No.
q squared, right?
No. Yeah, yeah,
Oh,
Right, there's other stuff here happening, right? So which part do you remember? You remember this one. This is a general result that tells you the nature of things. And what the nature of things tells you is that it goes with the square root of q of square root of SNR. Look at everywhere in these expressions, there's a square root of SNR. Now, if you remember q function is e to the x squared, right? So you have a square root times squared, so it is e to SNR, right? That's the nature of things, right? So there's that exponential there, right? Exponential to the signal to noise ratio. So that's how majority of this probability of errors behave. And a lot of times, so that's why we like to look at them in log plots. One log plot, just to I guess dBs on the x scale and log scale on this in dBs and a log scale on the y-axis, right? Because then they become kind of like almost linear.
Polynomial.
Almost linear. They don't become linear but like for high signal to noise ratios, they kind of end up being almost straight, like your waterfall curves, right? So the nature of this thing you remember, but in all actualities, as I said, in most cases, these are just your token examples to help you gain your feeling and to learn what you expect. In most cases, if you deal with this, you're going to have some of the modulation schemes that you're trying to it's going to be slightly different, or there will be the constellation points are going to be at some different locations. So in most cases, you will have to resort to simulations. You will have to kind of simulate this. And what I have here is I have a code that I wrote a few years ago just when I taught this class. Let's go through it, and I'll try to, in broad strokes, explain what it does. And the reason for that is I wrote this so long ago, I'll be happy if I remember what it is. But this actually generates those waterfall curves for PSK signal in AWGN. Go ahead.
So every time whenever somebody asks me about what is the probability of error in PSK, or from the previous lecture is about PAM, so the only thing that you remember is that if it's going to PSK, then you will have that the Q square root of SNR, and then if you're going with the PAM, so 2m minus 1 over m q over a over square root m over 2, and that's it.
That's the end result, right?
Yeah, that's the conclusion.
If somebody asks you that specific question, this is the specific answer that you give. But the thing is, you're not going to be asked that specific question. The question is going to be, design a system that has these kind of performance. And then you say, okay, I'm going to have this modulation scheme. This is a raw bit array. If I need to improve upon it, this is kind of coding that I need to design. This is kind of interleaving. This is, all of these other things that you put on top of it. So there's going to be, this very simple question that somebody asks you, there's a very simple answer, but the questions are not always that simple. What you're also going to find is that a lot of times you're going to go straight to the waterfall curves. And waterfall curves sometimes will come up with the analytical expression, like in these cases that we consider here, but a lot of times they will not, because a lot of times they will come from either measurements or simulations or however they manage to characterize your receiver. So a lot of times, you know, when you do, let's say, link budget evaluation or something, you're going to be looking up the waterfall curves to translate between signal to noise ratio and probability of error that you're trying to achieve. So let's take a look at what this code does, right? It generates the waterfall curves for PSK. You can see the final result on the next page, and this is the same as one of the figures in the book. You have EB over NT on or our famous EBNO on the x-axis, and then you have probability of error that is going to be on y-axis. Now let's take a look at how does this code work. Let's pick m. Let's say m is equal to 4. This result's just gonna this EBNO here is a vector that is going to go from 0 to 20. So that's in increment of 1 dB. That's your x scale. So I'm going to be calculating probability for every dB increment in your EB over power spectral density of the noise. Notice how large is this n is. N is, what is this? 1 million?
No. Oh yeah.
1 million. What does this mean? I'm going to be throwing 1,000,000 darts. Why is it necessary to throw 1,000,000 darts? Because if you look at the scale here, the scale goes, and even this scale is relatively small. It goes to the 10 to the minus 3. So if you're trying to simulate, let's say, to determine the probability of errors that are on the order of 10 to the minus 6 or 10 to the minus 3, or whatever, you have to make sure that you throw enough darts so that you capture the probability, right? If you're, let's say this equation predicts that you're going to have a probability of error 10 to the minus 6, then if I throw 1,000,000 darts, probably one on average will be misplaced. But then, you know, what if it happens then none? So I get the probability of error 0, or what if happens that it happened 2, right? So I'm already twice, my estimate is 2 times bigger than what it actually is. So you have to make sure that your number of darts that you throw is at least few orders of magnitude larger than the smallest probability of error that you're trying to quantify, right? So that's why this n is so large. So I go, for example, I go for every m. So let's say m is already picked. I pick a particular symbol here, and then plot here is just turning on and turning off the constellation. So if you make plot equal to 1 in the second line of the code, you're going to get constellation plotted, and I assume you're going to have also those clouds that I talked about plotted. And then here I generate n0 based on a EBNO ratio that I have. And then I set error counter equal to 0. And then for k equal 1 through n, I'm actually throwing darts. Right? N is the number of darts. Every time I pick a symbol, that's this symbol Sm, I determine sigma, or that's a standard deviation of the noise that I have. Then I determine n, which is the sample of the noise, and look at this rand n, that's a random number generator with a normal distribution. It is already 0 mean, so me just multiplying it with sigma generates the random number distribution that has a 0 mean and standard deviation of sigma, and sigma is equal square root of n0 over 2. If you go upstairs, you can see that that's the standard deviation of the noise. So I'm throwing darts. You know, I already generated the received vector, that's this r. Then I compute the distance between the received vector and all the symbols, and I assign this, then I determine which symbol it is. And then I ask the question, is the received symbol different than transmitted symbol? This is this question, if j is different than I of 1. If it is, then I increment the error. I've thrown the dart and I made an erroneous decision. And I keep on throwing darts until I'm done with capital N darts. And at the end, I say results of ij, which is the result of the given EB over MT, and for given constellation, is equal to the number of errors that I've counted over total number of darts that I've thrown. And I do that for all EB over MTs, and then I generate a plot, and this is the plot here. You know, what I suggest is you type in this code, you know, kind of step through it, and then experiment with different n to get a feel about, you know, this statement that I said. Because if you set n to be too small, you're going to notice that these curves are not nearly smooth as they appear to be here.
Excuse me, N or N? N, right? The
N, capital N. Capital N, the number of darts thrown.
number of them.
Okay, it's not the best code, but this is essentially how you would do this in practice. In more complicated modulation schemes, you know, you might use tools like Simulink, or you might use more elaborate tools, but essentially the problem of calculating probability of error is relatively easy, as I said, conceptually, and then it is typically done through some sort of tool. Okay? Any questions here? All right, so what we've done, go ahead.
So whenever you increase the number of n, there will be, and then what happens with the n actually? If I shorten, like decrease the number of n, and then I want to have a larger scale of n, so what will happen?
N is the number of darts. That
Yeah.
has nothing to do with M. M is the number of constellation symbols. Right? What you will notice here, and these curves show that clearly, is one of the behaviors that I taught before. And this is as your M increases, M like a mouse, then you require progressively larger signal-to-noise ratio, or EBNO, to achieve the same probability of error. Let's take a look at 10 to the minus 2, and let's look at two curves, m equal 4 and m equal 32. You can see that for EBNO equal around 5 dBs, you get 10 to the minus 2 probability of error for QPSK. But if you have 32 symbol QPSK, to achieve the same probability of error, you're going to need 18 dB, right?
Yeah.
And this is familiar concept to us on many levels. One is this view in a constellation diagram, which says as you have more symbols in a circle, they're closer to one another. Given the same noise, or signal-to-noise ratio, then it becomes more likely to make an error. But it's even more fundamentally clear to us using the Shannon's capacity formula. Because when you go to m equal 32, you're packing more bits per symbol. So your bit per hertz is larger, therefore to maintain the same probability of error, your signal-to-noise ratio needs to go, because you're getting a larger capacity, your signal-to-noise ratio needs to be larger.
So I have another thing. I just please correct me if I'm wrong. So whenever you have a calculate link budget, whenever you want to calculate link budget, if you want to increase the number of the constellation series, like the number of your EBNO, so it means you need to have a higher number of your gain. Like the
Yeah,
of gain.
yeah.
So higher number of the gain.
Yeah, correct.
Output will be
Correct.
high.
The question is, when you're doing your link budget, if you switch to higher level modulation scheme, meaning you're gaining some throughput, right? Because every symbol now carries more bits. You have to pay. And what is it, how do you pay most commonly? In power, right? So whenever you switch from lower modulation scheme to higher level modulation scheme, you have to increase the power. Now, the things usually go the other way around. You always, in the modern systems, all modern systems that we have, especially the ones that are meant to handle data, have what we call adaptive modulation schemes, which means that you've seen that the transmitter is a regular QAM transmitter, right? So it is the same, essentially, whether it's QPSK or 8PSK or 16 or QAM or whatever, right? You have I and Q branch and you modulate them with the proper magnitudes. So when you dimension system, you kind of dimension it for coverage, for the range, based on the lower modulation that you're going to use. So you're going to say, if this system works with BPSK, you can go 3 miles. And that means I'm going to cover 3-mile radius and have a ability to communicate. But then as I move closer to the source of transmission, my link budget improves, right? My power received goes higher. And the system is smart to say, oh, I have plenty of margin to now switch from BPSK to QPSK, and then give my user twice the throughput. Or go from QPSK to 16 QAM, give him another boost in throughput, and then go all the way to 64 QAM in some cases. And that's what happens, you know. We all know that if you want to have a good throughput, you need to have a lot of bars, right, somewhere. And that's exactly that, you know, because systems are getting smarter, that so that they have adaptability based on the signal-to-noise ratio that they experience. You know, and if you look at even further detail, there's always what we call measurement report of some sort, or channel estimation report, where the mobile or the receiver sends back to the transmitter a feedback saying, this is how good my signal-to-noise ratio is. And this is what I recommend that you use for the transmission. And then transmitters say, oh, okay, so here's higher throughput, right? Because it benefits the transmitter too. You know, especially in the case where there's a multi-user access, because then I can deliver all the data to this guy and free the resources for all the others. So all of this is kind of very, very real, even though it's a lot of math. You know. That's the beauty of communication theory. There's a lot of math, but it actually works. There are other areas where there's a lot of math, but then you just say, it's not like electronics. There's tremendous amount of math, but it's still 20% accurate at best. All right, so that's it for today. As of next time, we're going to start looking at what happens when your channel is bandwidth. Right? So far, we had a luxury of infinite bandwidth. Right? We didn't worry about it. We start worrying about it next time.